So these trigonometric identities and the compound angle formula I want to look at, hopefully we'll get a chance to look at this, but possibly not as we're running a little bit late. Start off just by reminding you of this wave function. So I've done a few pre-prepared slides this time, which I hope you're familiar with. If I were to plot this function, y equals a sine omega x, I'd get a sine wave, which you're familiar with. Omega represents the angular velocity. X would represent time, in this case, and a the amplitude of the wave. So that familiar wave, and I think the first part of assignment 4 is to do with that. Okay? So that's what we were looking at. Remembering the relationship between angular velocity and frequency in the period of the wave, which are these two little equations at the bottom. So carrying on from this idea, we can actually talk about these ratios, and if you remember, the sine ratio is to do with, if I were to take a particular angle, the position on the right angle, on a right angle triangle. So if I were to make a right angle triangle here, then this side, if this is the angle, the opposite side in a right angle triangle is what tells me the sine, isn't it? So actually what this wave is doing is tracking out for various angles what the sine of that angle is, what the length of the opposite side is. So we can write down those ratios, the trigonometric ratios, what the sine is and what the cosine is and what the tangent is. And then we can use that to make up a few more identities. And here are some trigonometric identities that you will come across, maybe. Tangent equals the sine theta over cos theta. So the tangent of the angle equals the sine of the angle over the cosine of the angle. And in a minute we're going to try and show why that is. And we could also show that something called the cotangent, and I will be defining these things, equals the cosine over the sine. So I thought it would be a good idea to start off by just writing down what these are. So you've got them to refer to, these identities. They're called trigonometric identities. So we're going to add to them. So wherever you make this note, leave room to put a few more, because there are quite a few of these identities that we can build up a list almost of these things, a bit like those differential things. That's right, yeah, a list of differentials, common differentials and integrals. So let's have a look at these identities and try and see how they're arrived at. They're useful in algebraic sense. They're useful for rearranging things. Just like the rules of algebra that we've been learning, we have some rules that you can use to play around with and rearrange trigonometric equations effectively. So that's what this is about, really, writing down what these things are. And as part of your assignment, you're going to be asked to prove one or two identities from some other identities that you know. So these sine, cosine and tangent ratios are our start point. Sine theta, in terms of that right angle triangle, equals what? That little ratio. Right, so sine theta, in terms of opposite, hypotenuse and adjacent, is opposite over hypotenuse. Cosine, adjacent, and tangent, opposite over adjacent. Okay. Those we're familiar with. Okay. If I were to divide sine theta by cosine theta, then I could write sine theta in terms of this ratio is opposite over hypotenuse. And then I divide that by the cosine of theta, which is adjacent over hypotenuse. So I can write that, opposite over hypotenuse over adjacent over hypotenuse. That's like one fraction divided by another. And you know what you do when you divide one fraction by another. What do you do? Invert the second fraction and multiply, right, Richard? Okay? So this equals the top fraction, opposite over hypotenuse, multiplied by the bottom fraction inverted, hypotenuse over adjacent. So I could write it like that. And then we'll see that the h's cancel. Hypotenuse side cancels effectively, and we're left with opposite over adjacent. Yeah. That's right, yeah. Works every time. Which we proved this identity, and so once we proved it once, it works every time. And what does opposite over adjacent give us? Tangent. So we have sine theta over cosine theta equals the tangent of theta, and that's one of those identities that you've just written down. This one here, tangent of theta is sine theta over cos theta. So it can be proved in terms of what we know about sines and cosines and tangents. And that's the sort of thing we do to prove identities. Now, a little definition coming up now. Sine to the minus 1 means the angle whose sine is theta. Let me just reveal the whole thing, might as well. Okay. Hi, Jack. Because sine to the minus 1 theta means the angle whose sine is theta, and you've got that button in your calculator. If you look at your calculator, the sine to the minus 1 is above the sine theta, and it means I'm going to work out the angle whose sine is. Is that right? Like an inverse function. So if I want to work out what the sine of 30 is, I type that into the calculator. If I want to know what the angle is, whose sine is that, I did the inverse sine button, sine to the minus 1. So sine to the minus 1 of theta does not equal 1 over sine theta. Do you remember when we talked about laws of indices? Negative power means 1 over, doesn't it, the inverse? But not with trigonometric identities, because that has a different meaning. Sine to the minus 1 means the angle whose sine is, or the angle whose cosine is. So we need another, something else, to mean the inverse of sine theta, or cos theta, or tan theta. And that's where these other words that you've seen come in. 1 over sine theta is defined as, that's what these three lines mean. So 1 over sine theta is written as the cosecant of theta, or cosec for short. So what does the cosec of theta mean? It just means 1 over the sine of theta, that's all. It's a definition. We can't use sine to the minus 1 because that means something else, so we use cosecant. And in a similar way, 1 over cosine of theta is called the secant, or sec for short, and 1 over the tangent is the cotangent. And when I first saw these, and nobody's been able to answer this question for me, I asked myself, well, why the heck don't they call the inverse of cosine cosecant? That seems to make sense, but it's not. For some reason, 1 over the cosine is the secant, and 1 over the sine is the cosecant. You have to just remember that. And 1 over the tangent is cotangent. That sort of makes sense. So, just make a note of these three definitions. 1 over sine is the cosecant, 1 over cos is the secant, and 1 over the tan is the cotangent. Yeah, if you want to make a note of the whole thing, I'll reveal it. If we go back and look at these now, hopefully they'll make some more sense. Tangent, sine over cosine. We've just proved that. Cotangent, remember cotangent means 1 over the tangent, so cosine over sine. It's the inverse. Secant, we've just defined as 1 over the cosine. Cosecant, 1 over the sine, and cotangent, 1 over the tan. So those are the first, if you like, 6 or 5 rather, trigonometric identities that people tend to use in an algebraic way with trigonometric functions, to play around with them. What I want to do now, though, is to use Pythagoras to prove another identity. So I obviously got a little bit carried away with my apostrophe there. Let's use Pythagoras to prove another identity. There's Pythagoras, a squared plus b squared equals c squared. And we can prove three identities with Pythagoras quite easily. A squared plus b squared equals c squared. What I do is I divide through by, say, c squared. So I could divide by c squared. That means to divide every term in that little in Pythagoras by c squared. Or I could decide to divide through by a squared. Or I could decide to divide through by b squared. And each time I get a different answer and a different identity. So I'll go through one, and then you can do one of the others and see how what that shows us. We can end up with 3 different trigonometric identities that we can then use. So if I divide through by c squared, I get a squared over c squared plus b squared over c squared equals c squared over c squared, which is 1. A squared over c squared could just as easily be written as a over c all squared plus b over c all squared equals 1. So I can write that. Because I've divided through by c squared, and c squared divided by c squared is 1. Anything divided by itself is 1, isn't it? Okay. Now, if we look back at our triangle, ABC, as written here, with that angle theta identified here, then in terms of sine and cosine and tangent, what is A over C? Adjacent over hypotenuse, which is cosine. So cosine, instead of in A over C, I can write the cosine of theta squared. Now, that would be a bracket round there, cosine of theta all squared, plus B over C. What would B over C represent in that rectangle, triangle? Opposite over, no, B over C. Opposite over hypotenuse, which is sine. So sine theta squared equals 1. So we end up with another identity. The cosine of theta squared plus the sine of theta squared equals 1. And by convention, to save putting these brackets in, we write this as the cosine of theta, and we might have talked about this before. If I put the squared there, that means the cosine of theta all squared. So when you write these things, a little 2 there means this, the cosine of theta all squared. If I write this, that means the cosine of theta squared, which is a different thing. That means the cosine of whatever theta is squared. What I mean is the cosine of theta all squared. So by putting a little 2 there, that's the convention we use to show that, okay? So rather than putting it in a bracket, we use that little convention. So this would be written as sine squared theta equals 1. And that is another trigonometric identity that you can add to your list. So you made your list of these identities, you can add that one. That's another one. The cosine of theta squared plus the sine, or sine squared theta, cos squared theta plus sine squared theta equals 1. Okay, now a squared plus b squared equals c squared. Divide through by a squared. And then look at what I've just done and see if you can come up with another identity. Right, so we've got 1 plus b over a squared equals c over a squared. But how can I rewrite b over a? And that's b is the opposite, a is the adjacent. What does that mean? What's opposite over adjacent in terms of tangent? So I can write 1 plus tangent of theta squared. So I put the squared inside there because I mean tan squared theta, the whole thing squared, equals, this is the awkward one. We've been discussing it over there. So somebody over here, c over a. In terms of this triangle, what does C over A equal? And which one is hypotenuse over adjacent? Sorry? Right, but not the cosine. Right, the inverse of the cosine. Cosine is adjacent over hypotenuse. We want the hypotenuse over adjacent, so that's the inverse of cosine, which is secant. So sec squared theta. And that's another identity. Okay? What are we going to do to prove the third one? And what do we divide through this time? By B. Right, so off you go. Okay? Divide through by B and come up with the last identity. There we are, third one. Dividing through by B, we get the last. So there's three identities that we can get from Pythagoras and from knowledge of what sine and cosine and tangent is, those ratios. Now, if we think about it, this is the sort of thing mathematicians do for proofs. Somebody has proved a long time ago Pythagoras theorem. So we know that works every time, Josh, as you were saying earlier. And we've defined these sine, cosine and tangents to mean opposite over adjacent and so on. Just using that basic information, we've now come up with three identities. And we know they're right, so we don't need to prove it anymore. We can write them down and use them. So if you've got those first five that we had and then these three underneath, you've then got 8 identities that you can then use to prove other things. So we add to our list. No, there's quite an exhaustive list. We're only going to look at a few. A bit like the differentials, we're just going to gradually build up our portfolio, if you like, of identities. So compound angle formula on your list of identities, so we've got the first 5 that we wrote down. Now you've just written down those other 3 identities. Here are 4 more called the compound angle formulae. So if you can put these underneath with it, of time really, more than anything else, and also because it's not really necessary, I'm not going to go through the proof of these things, but I have put a proof on the site. So if you look at the section on this assignment, assignment 3, is it, or 4? No, 4, assignment 4. You'll see in there a proof of the compound angle formulae, and it is basically just drawing out right angled triangles and splitting the angles up and proving these identities. And if you're interested, have a look. Okay, and you'll see that the same sorts of arguments that we've been using already to try to work out the ones we've already looked at are used in these compound angle formulae. It's not immediately obvious that how useful these can be. What it's saying is I can split. So if I look at this sine A plus B1, what it's saying is if I've got a sine of 2 angles added together, and I've used the example down here 30 plus 40 degrees, it can be split into the sine of 30 times the cosine of 40 plus the cosine of 30 times the sine of 40. And there may be uses for that. And in AC theory, later on, if you carry on with your studies, we look at things like Fourier analysis, where we split waves up. And if you go into the world of sound engineering and stuff like that, combining waves and splitting waves up into its constituent parts involves using formulae like this and dividing up your waves, so that you can then work out exactly what each complex wave is made up of, and then you can build up and play around with parts. So it's all about waves, different types of waves that you might see, and using these sorts of identities and formulae to study them, basically. And the reason why this is in the assignment and why it's in this course, I think, is because of that. So it's sort of like a standalone thing, learn about these compound angle formulae at the moment. Unfortunately, it sort of almost comes down to that. So as I've written down this example here, for example, sine 30 plus 40 could be written down as sine 30 times cos 40 plus cos 30 times sine 40, for example. Not that it's really necessary, but if you look at these, you can almost sort of imagine how you could remember them. Look, the sine ones always turns out to be sine A cos B and cos A sine B. And if you're adding them, you add them, and if you're taking them away, you take it away. So those two, it's sort of, if it's sine, sine, cos, cos, sine. If it's the cosine, the cos, cos goes together, and the sine, sine goes together. And note, if it's added, you subtract. If it's subtract, you add. So it's not impossible to remember these things if you ever want to or need to. Okay, but if you use these a lot, which you would do if you do a lot of sound theory and stuff like that, you'd get to know these things. Okay, because you'd use them. Obviously, anything you use, you tend to remember, don't you? So there they are. There they are, these compound angle formulas. Let's use these now to try and prove an identity. So we have to prove that the cosine of y minus pi, so angles here are measured in radians, not degrees, and usually that's the case actually, we measure angles in radians, plus sine y plus pi over 2 equals 0. We've got to prove that. So whatever y is, it's the same in both of these brackets. So we need to use the trig identities. Which ones are going to be useful? You've written about 10 of these now. Which ones are going to be useful, do you think? What can we do with this first bracket here?
Use the cosine a minus b.
Yeah, exactly right. We'd use this identity. We can split cosine of a minus b into this. So rewrite that first bracket using this identity. And then when you've done that, plus rewrite that using the relevant trig identity. So the first bracket could be rewritten like this. Now when proving identities like this, what we tend to do is we don't carry on and write the second one and put equals 0. It's not an equation in that sense. What we're doing is we're trying to prove, and this is what you'll be asked to do, we're trying to prove that this left-hand side of this equals 0. So all you do is you write down the left-hand side and play around with it. So the left-hand side, cos y cos pi plus sin y sin pi. And then, well, what we end up doing is we end up proving that that equals 0, and then we say we've proved it. Okay? So it's not like we're trying to play around with this equation by adding and subtracting something to either side of the equation. So you wouldn't, for example, take sine y plus pi over 2 over the other side or anything like that. You just play around with one side, generally the left-hand side, until it equals the right-hand side, and then you proved it. So that's the difference between solving an equation and a proof. You just manipulate one side of it until you can show that it equals the other side of it, and then you proved it. So left-hand side, cos y cos pi plus sin y sin pi. Just move this a little bit, because it's quite a long identity, isn't it? What do I do about the other one? Sine becomes sine cos, doesn't it? And because it's plus cos sine. So sine y cos, yeah, run out of room, pi over 2. Okay. Now we have to think about what the cosine of pi is, what the sine of pi over 2 is, and so on. So you could put it into calculator. However, I want to show you a way to do it without doing your calculator, using the calculator. Of course, you could always just use your calculator. We could work out, what the cosine of pi is. So actually, why don't we do that on the calculator? What's the cosine of pi? Make sure you're in radians. If we use a calculator, this turns out to be -1. So it's common, if you work something out, to put an arrow through it like this and put -1. Cosine of pi is -1. So we can do that. I want to show you, though, how that we could have done this without recourse to the calculator, and then see if we can do the rest of these, sine of pi, cos of pi by 2, sine of pi by 2, without using a calculator. We could quickly sketch a sine wave and a cosine wave. Sine wave looks like this for one complete cycle. Cosine looks like this for one complete cycle. Okay? In terms of radians, one complete cycle is What? 2 pi. Right, Josh. Okay. Yeah. 2 pi. So pi is there. Pi and the cosine one is going to be here. If we've got no amplitude, remember amplitude is the height up here, no amplitude measured, it must be 1. So this is 1, and this is minus 1. This is 1, and this is minus 1. Yeah. So what's the cosine of pi? Minus 1. Okay. What is the sine of pi? 0. What is the cosine of pi over 2? Must be 0. Okay. I've not sketched it very well. That should be halfway here. So 0. What's the sine of pi over 2? 1. And you could have done it in a calculator, but with a quick sketch on almost a knowledge of what these things are, you can do it. So I can actually now rewrite this. Sorry? Sine of pi over 2. There's pi. So, no, that's pi, isn't it? 2 pi, that's pi, John. Pi over 2. Yep. 1. So now, but well done for questioning it. I don't mind that at all. Cos y. So now I can rewrite this, each of these, because the first one is just cos y. Times minus 1. So that's minus cos y. The second one, anything times 0 is 0, so that's gone. Plus 0. The third term, anything times 0 is 0, so that's gone. And this one is cos y. And so now everything cancels out, and that equals 0, doesn't it? So therefore the left-hand side equals 0. And we then say that we proved it. We proved the left-hand side equals the right-hand side. And what do we do to write that? QED, which is Latin for I've proven it. Od est durandum or something like that, which means proved and proven. We've proved that the left-hand side equals the right-hand side. Yeah. So what did we do here to make this proof? Prove that this equals 0. So to do that, we don't write it as an equation. We just focus on the left-hand side and try and prove that that equals 0. So we rewrite the left-hand side by looking for trigonometric identities that will help. And the compound angle formulae help here, because we can split this up. And then we work out what we can. We can work out what the cosine of pi is, either by using a calculator or by remembering what these sine and cosine waves look like. So we can then go through and see that actually the second and third terms are 0, and the first and third terms give minus cos y plus cos y. So therefore the left-hand side is 0, and we proved it. But you've got a similar proof to do in your assignment when it comes to it. So looking at assignment 4, task 2, let's just check everybody's happy with the ideas here. A, use the compound angle formulae to prove sine 2 theta equals 2 sine theta cos theta. And the start point is the key thing on that, okay? So think about that. How can I rewrite the sine of 2 theta so the compound angle formulae can be useful? Because it says use the compound angle formula, so those are the ones you're going to use. Part B, use graph plotting software to show that the identity in A is true. So what I'm asking you to do here is actually just plot sine 2 theta and 2 sine theta cos theta and show that the waves are the same. You get the same answer. C, another one using the compound angle formulae and this identity that we've proved already, sine squared theta plus cos squared theta equals 1, to prove this. Cos 2 theta equals 1 minus 2 sine squared theta. In B, that's for the graphs, yeah.